Good morning, everyone. I'm sure you've noticed that I am not Andy Ruina, but I will be giving this lecture anyway. Yay. Okay, so last class we talked about using angular momentum balance to describe the motion of something that's not rotating. Today we're going to use it to describe something that is, but is a point mass, because point masses are easier than distributed bodies. But before we get into that, let's review the laws of mechanics. So we've been using this a lot this semester, which is linear momentum balance, which in vector form is the sum of external forces is equal to the mass times the accelerations. So with multiple point masses, we can write this as the sum of each mass times each mass's acceleration, or as the total mass times the acceleration of the center of gravity. Similarly, for angular momentum balance, we like to write the sum of moments about some point C is equal to the sum of the change in angular momentum about point C. With point masses again, we can write the sum of R cross MA. And with distributed masses, we can write the integral of R cross A dm. So were these, oh. Okay. So this is relative to an arbitrary point C, but we would like to write this in a way that seems similar to this, where we can talk about the motion of the center of mass and then any motion that's around it. So we can rewrite this R cross M total, the acceleration of the center of mass. And then we need to also have the motion relative to the center of mass. And so this is again for point masses. For distributed masses, we want an integral so we like to call this the angular momentum relative to the center of mass. And fortunately, in 2 dimensions, which is what we're working in right now, we can rewrite this term as moment of inertia about the center of mass times the change in angular velocity in the k-hat direction. And that's because we're working in the xy plane, so any rotation is going to be in either k or negative k. So let's try using this for things that are actually rotating. And we're going to talk about the constrained motion of moving in a circle. You might think that moving in a circle is simpler than moving generally in all directions, but the constraints do add some complexity to the problem. So we're going to look at the classic example of a simple pendulum. So we have a mass, and it's connected to the ceiling by an ideal string, so a massless, extensionless string. And then for this problem, we want to define our coordinate system like this, where x is down and y is that way. So we have our unit vectors like that, and then we have this angle, which we can call theta, and then the string has some length L. So the reason we pick coordinates in this format is so that we can have gravity in the positive x direction, and all of the standard trig relations look like we expect them to, which is nice. So what we want to get is the equation of motion, which we can write like this. So we have theta dot is equal to minus g over L times sine theta. And then we can also write it as two first order differential equations. If we set theta dot equal to omega, and then we have omega dot equal to minus g over L sine theta. So once we get to here, we'll be able to plug it in to MATLAB and solve for the motion. While this equation looks temptingly simple, it's actually pretty tricky to solve by hand because it is a nonlinear equation, which is why when you're first learning about the simple pendulum, we linearize by only looking at small theta. Here we're not looking at only small theta, we're looking at all theta. So we really need to keep the nonlinearity. Okay, so now we want to actually find the equations of motion. So let's draw a free body diagram. We have a mass that's in gravity. We have a string that applies some tension force. And now we can set up a new coordinate system that looks like this. And we're going to call this ER hat. And we're going to call this E theta hat. So both of these are going to change as theta changes. So we're used to having coordinate systems like this that are fixed in space, and then we don't have to worry about how the unit vectors are changing when we're trying to solve for motion. Here, the unit vectors are changing, but this really simplifies how we write the other pieces of the problem. So what we're going to do next is take the angular momentum balance about the origin. So this is our origin, which makes sense because that is what the simple pendulum is moving around. So we write the sum of moments is equal to this quantity h dot, and we know that our only moment is going to come from gravity. So we have the radius, and our center of mass is going to be exactly where our mass is because it's a point mass. So we have R cross F, and in this case, F is mg I hat. And this is positive because that's how we defined our x. And then we have, this is equal to R of g relative to O crossed with mass and the acceleration of the center of mass. So the tricky part of this problem is figuring out what this actually is. So let's figure out what it is. So we know what the radius is because it's simply L along ER hat. ER hat always points along the string. The mass is always L distance along the string, so we have our radius is always this. So let's take the time derivative to get velocity of the mass. So we want to take time derivative of this quantity ER hat. And now we know that L isn't changing because that's the whole point. But ER hat is changing. So let's figure out how it changes. So we have our unit vectors, ER hat and E theta hat, at some point in time. Sometime later, ER hat is here. So this angle is theta, or this angle is delta theta, and this vector here is delta ER hat. So we want delta ER hat over delta t. And we have, well, so we know that this, so if we take the limit as delta t goes to 0, we have that delta ER hat goes to delta theta in the E theta hat direction. So in the limit, we have theta dot E theta hat. So just to write that more clearly, we have the time derivative of r is L theta dot E theta hat. So now we want to take another time derivative. Because we want the acceleration, which is the time derivative of the velocity. So this is time derivative of L theta dot E theta hat. And taking the product rule, we get L theta double dot E theta hat plus L theta dot, and now we need the time derivative of E theta hat. So again, looking at this picture, if the coordinate system has rotated by some delta theta, now we have a new E theta hat over here. And I drew this. Yes?
Can you explain how you get ER hat dot equals theta?
Yes. So this is, so right now I'm doing kind of the hand waving argument. A little later I'm going to derive it using I hat and J hat. But so if you think about the path of this point in time, if it's rotating this way, which would be a theta dot greater than 0, the end of this vector is moving in a circle, and the tangent to the circle is perpendicular, and we already know that perpendicular at this time is going to be E theta hat. So it's moving with rate theta dot, and since it's always a unit vector, in the limit as delta t goes to 0, it's going to be exactly perpendicular, so that's exactly E theta hat. Okay, so now we have delta E theta is going to be in the minus ER hat direction. So that gives us, for acceleration, L theta double dot E theta hat minus L theta dot squared ER hat. So now we have what the acceleration of the center of mass is. So we want to plug that back in to our angular momentum equation. So that gives us L ER hat cross MPI is equal to L ER hat crossed with M. Now we have L theta double dot E theta hat minus L theta dot ER hat. Okay, so let's do this cross product. We have ER hat like this, crossed with I hat, which is down, so that gives us a negative K, and the angle is theta, so that gives us minus L M G sine theta K hat. And this is going to be equal to, so we have ER cross E theta hats. So that's M L squared theta double dot K hat E theta ER cross E theta is K. And then we have ER cross ER, which goes to 0, which is nice, because now when we dot with K hat, we get and divide through by ML squared, we get theta double dot is equal to minus G over L sine theta, which is what we wanted.
Excuse me?
Yes. Oh, sorry.
Can you explain how you got the minus sign on L being dot squared over there? You just sub in the what you got for
Oh. So where did I? Oh, so E theta hat dot is equal to minus theta dot ER hat. And you can see that for this picture by a similar argument as before. With positive theta dot, E theta hat is going to be moving this way, which is still perpendicular, but in the minus ER hat direction. So now I want to talk about polar coordinates in a slightly less hand-wavy way. So we have our Cartesian coordinates arranged like this. And we have ER hat and E theta hat. So if we want to write ER hat in terms of i's and j's, where this is theta and this is also theta, we have ER hat is equal to cosine of theta times I hat plus sine of theta times j hat. You can see that from this nice right triangle. Pretty straightforward. And now we want to write E theta hat. So now we have this right triangle. So this is going to be minus sine theta I hat plus cosine theta j hat. So now we want to take the time derivatives. So we get ER hat dot is equal to, using the chain rule, we have theta dot times minus sine theta I hat. And remember, i's and j's aren't changing. Plus theta dot cosine theta j hat, which we can pretty immediately see that this is theta dot E theta hat. And now for E theta hat, time derivative, we again do the chain rule, or yes, chain rule. So we get minus theta dot cosine theta in the I hat direction plus theta dot sine theta in the j hat direction, which is minus theta dot ER hat. Does that make sense? Anybody have a question? Yes, because that's how the derivative of cosine works. Okay. So now, if we look back at this cross product, we can write ER hat in terms of i's and j's. The I term goes away, and we're left with sine theta j hat crossed with I hat. So that's going to be a negative k hat, and we still have the sine theta, and that's how we got this. Okay, let's do some more mechanics. So we just did angular momentum balance. Let's do linear momentum balance. So now we have the sum of external forces is equal to n total AG. So our forces are gravity in the I hat direction, and then we have tension in the minus r hat direction. And this is going to be equal to mass times the acceleration in r hat, er hat, plus the acceleration in e theta hat. So here I've just pulled out unit vectors from this, or the components in each unit vector. And so we know that this piece is going to be equal to L theta dot er hat plus L theta double dot. Oh, and this is squared. E theta hat. This should also be squared. Okay. And I forgot to close my parentheses. So we have a vector equation, and we want to split that into separate equations. So first we dot with er hat. So we want to take this and dot with er hat. And that gives us mg cosine theta minus t is equal to ml theta dot squared. And then we want to dot it again with the theta hat. And that gives us minus mg sine theta is equal to ml theta double dot. So we can rearrange this, and we get the equation we were looking for. And this equation is enough to completely define the motion in the system. But now we have additional information, which is what this tension force actually is. So we can solve for that. And we have the magnitude is mg cosine theta minus m of theta dot squared. So this is obviously just balancing out gravity. And then this term you can recognize as the force necessary to contain it in circular motion. And I saw a question. Yes? Yes. Thank you. Yes, and that, great. So now we know that the tension vector is minus t. Is minus t in the r hat direction. So if we need to pick a string or need to contain it, we have some way to figure that out. Yes? So this, so this is separate. Right, so I took the equation on that side and dotted it with the r hat, and then I took that equation and dotted it with e theta hat. And that gives us the forces in each of the two directions of polar coordinates. Are there any other questions? So we have this nonlinear equation of motion, and it would be good to think about what that means in terms of the actual motion compared to the linear model. So we know that for small theta, sine of theta is approximately equal to theta, and cosine theta is approximately equal to 1. And then if we look at the motion over time, you get a nice, pretty sinusoid. So if now we have the full nonlinear model, something happens to the motion. And it's no longer exactly a sinusoid. So which way do you think, or do you think the period will increase or decrease because of the nonlinearity? Okay, think for a moment. And now we're going to vote with our hands. Okay, so if you think the period will be shorter, meaning the pendulum will swing faster, raise your hand. Okay, and if you think it'll be longer. Okay, so the answer is it takes longer. And you can think about it like this. So with a simple pendulum, we're not really restricting theta at all, right? So let's imagine it starts like this. And now instead of a string, it's a rod, so it doesn't squish and do weird things, right? So this is still always L, and we have a mass like this. And it'll swing back and forth, where it goes like that, conserving energy. And now let's imagine we start it like this. What is the period? I heard 0. I also heard infinity. And yes. Well, so now I changed it to a rod, so it makes sense, and it's still circular. So if this was exactly ideal land, then the period would be infinity, and the frequency would be 0, because it could balance up here forever. But this is an unstable equilibrium, so in real world, it would eventually perturb itself and fall down. So this is the extreme case where the period is much, much larger than it would be if the linear model were still true. So that means for relatively small thetas, you could expect it to be very similar and then slowly drift, kind of like this, except I'm bad at drawing because the amplitude should be the same. Does that make sense? Does anyone have a question? Are you getting very sleepy? Yes? Oh, so if we, sorry. So really, so if we start them at the same initial theta, the linear model would be like that. So both models conserve energy. So if we start them at the same amplitude, then they're still bounded by that amplitude. But the nonlinear model will have a longer period, so it'll slowly drift in phase. Yes? So it's a smooth function, right? So if we start both at 0 with 0 velocity, then the answers are exactly the same, and it's really boring because it's 0. And if we start it very, very close to 0, so theta is really, really small, then they'll be very, very close. But then in the limit, where theta is as big as it can possibly be, we get completely different answers, right? We get no motion or a giant sinusoid. Does that address your question? So in between, it'll take moderately longer to fall. Yes?
Is there a way to calculate that
So you can pretty easily do it numerically, right? Because we have the equation of motion to plug into MATLAB, and then we can also plug in the linear model and then measure the difference. Right, so analytically, you need to have a solution for this, and that is a hard problem that would take me a really long time to solve. Yes?
With the nonlinear model, would the graph of theta against the perfect sinusoid?
For the nonlinear model? Right, so it'll look kind of like a sinusoid, but the non-sinusoidalness is where the period comes in. Okay, if there are no further questions, then I guess we're done.